This is a brief overview of our paper covering a solution for unified system modeling, published in the ASME Journal of Computing and Information Science and Engineering. The purpose of this paper is to introduce a new modeling framework called a constraint hypergraph. It describes how it can be used to combine system models and shows how the system elements are related to each other. A constraint hypergraph breaks out the behavior of a system into discrete objects. We can represent behavior as a set of constraints, constraining the value of a state variable based on the values of other variables in the system. For example, the variable k over m is constrained to be the result of dividing m into k. Mathematically, this is a function, mapping each pairing of k and m to a value in the set k over m. Similarly, x double dot is constrained by a function mapping each pair of k over m and x. We represent each variable as a node and each constraint function as an edge. These edges are usually multidimensional since most of our relations are unary, resulting in a hypergraph. These edges can be integrated into larger hypergraphs that show how systems can be combined. This graph adds damping behavior to the previous slide, resulting in a simple model of a mass spring damper. The graph format encourages interoperability, with the combined models revealing the behavior of the aggregate system. The reason for this is due to the composability of functions. Any two functions that share domain and codomain can be composed immediately without losing any information. This is shown here, where the relationship between variable a and variable c is given by the composition of functions f and g. The composed functions match every element in A with an element in C, allowing for sets to be related to new sets, such as B, without fear of losing information or invalidating a constraint. In addition to modeling, the hypergraphs offer powerful abilities to simulate a system. Simulation is the artificial identification of a system state. We can do this by predicting the value of an unknown node based on its relationships to other known nodes. Every edge represents a simulatable pairing. Function g allows us to simulate c for any known value in set B. Similarly, if a value in set A is known, then the value in set B can be simulated by calculating function f. Because these functions compose then, edges can be chained together to show how some variables relate to other variables, for instance, how A relates to C. A chain of functions results in a tree structure. A tree where the root of the tree is the simulated output node, and the leaves of the tree are the known inputs. Simulation chains are equivalent to finding paths through the hypergraph. Every path represents a set of inputs that can be used to simulate another node. This makes simulation far more flexible. An imperative framework such as a block diagram can only be simulated in one direction. There's only one possible pairing of inputs and outputs. A constraint hypergraph, on the other hand, represents every possible pairing of input to output. The analogy that we use here is the difference between getting a list of driving directions that take you from one city to another versus having the whole map. A map gives you the directions for every city, between every city, because it shows how every city is related. Similarly, a constraint hypergraph shows how every system variable is related to each other, allowing you to simulate between any given variable. Now, there are some technical challenges with such general simulation. The biggest ones, namely dealing with cycles and also model validity frames, are treated in our paper with a little bit more detail. Our paper also discusses pathfinding strategies, how edge weights can be used, and how we can represent model uncertainty, computational runtime, and other factors that are often difficult to deal with when doing system modeling. We conclude the paper with a demonstration of a more complex system, in this case an elevator lift system. The constraint hypergraph here combines models from three different domains. One, a discrete event simulation, shown in the bottom left, a PID controller in the top left, and a dynamic model of the elevator's forces on the top right. As can be seen from the graph, constraint hypergraphs are not very good for visually representing a system. They are complex, often cluttered, even not very readable. What they do excel at is being machine readable. In this case, once the graph is set up, it can be simulated in any direction by a specifically designed pathfinding algorithm that uses a breadth-first search to find viable simulation paths. We provided such an algorithm as an open source library that's available in beta form on the Python package index. By using a constraint hypergraph, behaviors can be expressed and simulations conducted for systems of any domain. With API calls, hypergraphs can even include analytical software such as CAD and FEA tools. Rather than resulting in a proprietary closed system, constraint hypergraphs are a mathematical basis for a uniquely open, integrated, and simulatable system model. We're excited about the potential of such a framework and invite you to follow along with us and investigate for yourself how constraint hypergraphs can be useful to you in modeling otherwise unconnected systems. You can find the GitHub repository for our solver at the given QR code, as well as more examples of constraint hypergraphs. Thank you.